I wish we could all be present, right? But not maybe later in the semester it will be possible. Hopefully, we'll see. Maybe not. Yeah. All right. So what I want to do today is try to have a little bit more of a focused class. And hopefully in the second part, I will have time to discuss a little bit new results on mean field limits. But for the first half, I'd still like to explain in very general term what's going on, what we're trying to do, and some models. And so let's start with what this is about, right? The basic question. And what happens is you take a multi-agent system, and in general, the kind of system that I'm going to look at is something like this. Right, so it's a very elementary in terms of the structure. So what do you have here? You have 2 by 2 interactions, right? With this K of X, which is an interaction kernel. Okay. And so we have pairwise interaction between particles. Then I put some diffusion, right? And so the Wi are n independent Brownian motion. Now, you might want to kill the diffusion, so you can take sigma n equal to 0, you can take a positive sigma n, you can take the diffusion coefficient independent of n, it can scale with n. In general, you expect sigma n to be some sort of matrix, and it could even be something that is not a constant matrix, so it's something that depends on the position. I'm really not going to discuss that today. Can get a lot more complicated. And all right, so this is a very basic model, and it covers a lot of physical, biological processes. I'll discuss some examples a little bit later, so we can be a bit more precise there. The big point here in this model is this factor 1 over n. And that's what makes all the difference between mean field and other type of mesoscopic or macroscopic limits, right? And Louis discussed at length the collisional models. And collisional models, there was this interesting question: what kind of equation does a gas actually follow, right? And well, I don't really know the answer either. What I know is that it doesn't depend on so much on the choice of K, so the choice of interaction kernel, the choice of diffusion, no diffusion. A lot of the structure that you get in the end depends on your choice of scaling. And there are tons of them, which is something that, again, I'll discuss when we talk about models, because then we can be a little bit more precise as to where this comes from and what are the whole zoology of models that you can look at. At at this point, what I am going to say is a relatively basic remark, right? What does this 1 over n do? Well, what it does is it makes this sum here, right? The sum over all the interactions, the sum has n terms, you divide by n, so it makes it into an average. So at least formally, the sum is of order 1. And essentially, another way of saying that is the mean field scaling is probably the simplest interesting scaling that you can put on the system. So, for example, if I put something that is less than 1 over n in front of that sum, right, what I'm expecting is that asymptotically the interaction will vanish, right? So if I have a lot of particles, then the interaction term probably doesn't matter too much, at least at first order. So the whole dynamics is dominated by diffusion, and therefore it's not super interesting. On the other hand, if I was putting something here that was much bigger than 1 over n, right, asymptotically the sum would formally diverge. And so then, very likely what you have is a very complex dynamics where particles will try to build themselves into configurations so as to balance the force on all of them. And that's a lot more complicated. It's very interesting, but it's a lot more complicated. So again, it's useful to think of this mean field scaling, at least from a math point of view, as, well, that's the simplest one where we still expect to see an interesting dynamics over times of order 1. All right. What's the issue with the system? Well, the issue with the system is the same as with all the systems of particles, right? N is typically very, very large. Oops. And so what you end up having to do is you end up having to solve a system of coupled ODEs or coupled SDEs in a very, very large dimension. To give you an idea, again, that depends a little bit on the application, but it's not uncommon in physics, for example, to have n of the order around the Avogadro number, so 10 to the 20, 10 to the 25. Right? So very obviously, you're not going to be able to even solve once a coupled system of ODEs with 10 to the 20, right? The best that I know people can do is around 10 to the 14, which is already super impressive, but still very far away from this kind of numbers. And on the other hand, you might also want to solve this more than once. And this makes it coupled with another issue, which is we do not know very well the initial data. Because basically there's no way to measure accurately even the position or position and velocity when we are going to look at kinetic models of that, right, of 10 to the 20 particles. Right? This is simply completely out of reach. So, so what do we do about this? Typically, then people like to take random initial data. Right. And there's a very important example here, which are chaotic initial data or chaos, right? And this refers to the molecular chaos that concept that was introduced by Maxwell in the mid-19th century. And so what this means is that the xi0, right, are IID according to some law. F0. And this is so this is very attractive, of course. The question here is how realistic this is from a physical point of view, or from a mathematical point of view. And of course, from the physical point of view, it's not easy to say. Certainly, the notion of molecular chaos is something that appears to be reasonable for gases, for plasmas, and for quite a few other models. But to say that this is always true is more than I can do. From a mathematical point of view, another way of thinking about that is to say that this initial data actually comes from another process, right? Because if you're doing an experiment, then that means you've prepared your experiment. And so the initial data is the result of the preparation of this experiment. And then one possible way to justify this kind of initial data is if you were capable of proving good ergodic property on whichever process led to the initial configuration. For most of many particle dynamics, of course, we have no idea how to prove something like that. So this is an issue on its own. But that won't necessarily concern me much this morning. So I will simply start from something like that, right? Assuming that, okay, well, we can take this. Now, this leads to an interesting observation. First of all, we've probably just made solving the system more costly. Right. Because if I tell you that the initial data are random, then to get the reasonable idea from numerical studies of what the system does, you would need to take a lot of initial data, right? Because you want to be sure that you'll have enough of them that they reasonably represent the whole distribution. So you don't have to solve once, you have to solve a lot. And that's the first issue. The second observation that is connected to that is, of course, if the xit were also IID, everything would be simpler. That's because if you're only interested in the statistical distribution of the particles, then you have an IID system, you actually only need one function to represent it. Right, and let's call that f of t and x. Okay. So that would be ideal, and that would be very, very nice. And now, instead of having a very large dimension system, well, you would have to find an equation on this one function. And that leads us to the notion of mean field. Because if you look at the one complicated object in our system, which is this interaction term, right? Because the Brownians are independent. Well, let's assume that all the particles are IID. Then this is, we can use a law of large number, right? This then would be well approximated by the following integral. Now, notice that that I is fixed, okay? So I'm using here the independence of every particle except I, and I'm throwing away the self-interaction, so the case J equal I. Okay. Very, very nice. The new equation now, let's call it, let's put a bar on it, right? The new equation would now look something like this. And this is called a Vlasov process. Right? Under this form, it was first introduced by McKean, precisely for this purpose of doing mean field limits. And from the PD point of view, that we are probably more comfortable with, right? You can immediately deduce out of that, again, at least formally, everything is formal so far, right? You can immediately deduce from that an equation on F, on the law. And if sigma n is a matrix, it's not sigma n square. It's sigma transposed as usual, of course. And by extension, this is sometimes called a Vlasov equation, even though strictly speaking, this only applies to the kinetic case. All right, so this is the whole idea behind the mean field limit. That's replacing this initial very large coupled system of ODE or SDE by a simple low dimensional PD or process, right? Depending on your preference. And again, it comes from this idea of mean field that if we have that VXI where IID, then we could replace the discrete interaction by its mean, more precisely conditional expectation here, and then everything would simplify. Now, you might say, okay, so we only have to prove that VXI are IID. Of course, they are not, right? Not only are they not IID, they cannot be IID. And that's because there are interactions between them. So necessarily you have correlations. it's impossible that you have zero correlation, actually zero correlation in a system like that. And that's where the whole difficulty emerges. What you have to prove instead of that is the notion of propagation of chaos. In the following sense, the xi are almost IID. And now what I have done is I have changed a question that is very straightforward and has a negative answer to something that is supremely messy. Because what do we mean by almost? Almost in how do we build a distance, right? How do we compare this kind of things? And there's an infinite number of answers. And as we will see in particular in the second part of this presentation, there are several ways of defining specifically what we're trying to prove by proving propagation of chaos, and which method and which way you're going to choose impacts what you can do. All right, so this is what we will discuss later. Now I'm going to talk a little bit about models, but maybe I should stop 1 minute if there are questions on any of that. And that's super elementary, but so most of you probably know this well. I think it's all good. Models. Oops, sorry. And so there's a lot of them, right? At this point, multi-agent systems are found essentially everywhere. So there's simply no way that I can even give a reasonable overview of the kind of models that you can end up looking at. So what I've done instead is I'm only going to focus on a few very classical ones. And the first one is the dynamic of point masses or point charges. So point masses is probably well, certainly the first many particle system ever written, probably among the first ODE ever written as well, because it dates back from to Newton. And so it's a very simple model for the celestial dynamics, where you consider a distribution of masses, but you reduce each one of them to a point. So what you need to tell me is, give me the mass of each one of them, the position, and the velocity. And then you can write Newton's dynamics. And so typically there's no self-interaction here, and then it reads something like that. You have a gravitational constant, you have mi, then you have k, and again, sometimes some possible diffusion. Now, Newton didn't have diffusion, of course, but right. And k here is the Poisson kernel, right? So k of x is equal to in any dimension larger than 1. All right. So this fits very well within the previous framework, with a few exceptions that I'm going to discuss right now. But first, let me talk a little bit about this diffusion, right? You notice that I only have a diffusion in VI, right? So that means that this is actually not the same sigma n as before, right? The sigma n before was a matrix, and the first diagonal matrix, and the first part was 0, and only the second part had non-vanishing coefficients. And this, for example, represents random collisions on interstellar gas or material, right? All right. Now, there are two big points here that that we should emphasize right away from the point of view of the modeling. The first point is that particles here in these general formulations are not identical. Contrary to what I had written above, right? Wait, it's not mi, it's mj, sorry. And that's because you see that there are different coefficients mj, right, into the equation. That's because they have different mass. Now, technically speaking, that means the corresponding system is not exchangeable, right? And in the sense that, for example, if I was looking at the joint law of this process, then this joint law would not be symmetric in general. And that can be very trivial or completely intractable depending on what you're trying to do and which approach you're taking. Usually people don't pay a lot of attention to that, and I think we're wrong. There are plenty of methods for which having a non-exchangeable system instead of an exchangeable system doesn't change anything. And there are plenty of methods for which, well, you can't apply them anymore. So I'm really not going to have the time to go much in depth on this point. I just want to raise it so that, again, you're aware that the initial system is probably non-exchangeable, and that might be a problem. But for simplicity here and now on, let's take all particles to have the same mass. Now, the second point is, of course, why a mean field scaling? Okay. And, well, there's no particular reason. I can actually do a rescaling here in this problem. And so what do I have? Well, initially, right, we have a distribution, right? So we have the xi0 and the vi0. So if I want to do a proper rescaling, this fixes the length scale and this fixes the velocity scale. In other words, if I want to start with a system where the xi0 are all of order 1 and the vi0 are all of order 1, I have no choice but to rescale x by L and to rescale vi0 by v. And if I want to keep this relation that the time derivative of xi is equal to vi, well, I have no choice, right? I also have to scale time by the corresponding ratio of the two. Really no choice in any of that. And so if I'm doing all of this, right, then I have zero choice, right? Let's use bar to denote the rescale equation. Then this has to be rescaled as well. That is it, right? And so what I have here is M. So plus a new sigma n, not write what it is. And you'll notice that K is homogeneous, right? By the way, I think sorry, got the wrong power. It's homogeneous of degree d minus 1. So I get something like this. Okay. And there's no particular reason on Earth why this m divided by v square ld minus 2 should be of order 1 over n. So again, here you have a textbook example of why the mean field scaling is just one scaling. It's relatively simple because I have a homogeneous K. So the L that was in the K, I can pull it out. Right? In general, if you have screening effects or if you have anything that is non-homogeneous, it would even be worse than that because I will not be able to put the whole of the scale in one coefficient in front of the sum. Again, here, is the mean field a good model or not? Well, it depends, right? It depends on the physical case. At least I can express it in a relatively straightforward manner in terms of all the rescaling. All right. The derivation of the mean field limit in that case is still mostly open. And I'm reasonably optimistic that in the case with non-vanishing diffusion, I should be able to do it in 2D now. But any other case, in particular 3D or no diffusion, I think it's fair to say that nobody has any idea how to do that. Just to give you a very a brief hint of why this is so hard. Even the dynamics for fixed number of and low number of particles is not simple in that case. And so you have a very natural open question, right, here, which is the dynamics well posed? Why am I asking that? Well, I'm asking this because I have a system of, again, of ODE or SDE, and my kernel has a singularity, right? So whenever two point masses are going to occupy the same position, then I have a blow up, and then I have an issue. And with two particles, right, we have explicit solutions. So we see that this can happen only when you throw them against each other, right? So, so what happens is the dynamics is well posed for almost all initial data. So let's correct a little bit the question, right? Well, so n equal 2 we know, right? We know it for n equal 3, for n equal 4. We do not know the answer to that if n is larger or equal than 5. All right, there's a variant of the system which corresponds to point charges. Right. Then I need to add the charge of each particle, right? And the equation on the velocity changes a little bit. There's a normalization constant, then there's k of xj minus xi. So I actually change the sign. For the same k, right? K equal Poisson again. Now, this is a little bit simpler, at least for fixed n. If all charges are equal or at least have the same sign, and that's because then the interaction is repulsive. Right, so for example, you have an energy here. Which, assuming everyone is the same, reads in the following manner. And find now is the fundamental solution to the Laplacian. So there's a constant, of course. So in general, it has this kind of form, except in dimension 2, where you have a logarithmic singularity. And what you see is that since the energy, at least with no diffusion, is nicely propagated, then this controls possible collision in the system. So at least the well-posedness is taken care of. But again, the mean field limit is fully open. And in both cases, of course, this mean field limit has a very similar form. And it's the Vlasov-Poisson equation. Which reads something like that. So you see again the degenerate diffusion, and of course notice that since in the interaction, right, the sum only involves the position, then the convolution here in general is with the macroscopic density, which is the marginal of f once integrated in velocity. So historically, the Vlasov-Poisson equation is very important. It was introduced by Vlasov in the 30s. Actually, first for plasma, so first for point charges, and then for gravitational systems. And it's the first example of mean field limit that was written. So it actually started with this equation. It's not the simplest one, even actually proving its well-posedness is now well understood, contrary to the Boltzmann equation, as you guessed from Rui's course. And but it's non-trivial. And in particular, in dimension 3 and more, showing that you have a classical solution to this equation requires a little bit of care. I'm really not going to talk about this, but just pointing out that this is not entirely straightforward. There is actually a comparable case in dimension 2, which are point vortices. And this looks a little bit like that. So the idea now is that you're going to represent or try to represent the dynamics of a fluid by putting discrete vortices everywhere. Right, so what you need now is you need the vorticity of it, right? And you need the position of the center. Now, if you use Biot-Savart law, this tells you that the velocity created in the fluid by one vortex, right, vortex number I. This is actually, again, under a very similar form as before, because it's Wi, and then x minus xi divided by x minus xi square, and this I have to rotate, so I'm going to use the notation perp, which, you know, in dimension 2, x perp is really just the rotation by pi over 2. So it's this. And then you get the following system. Right, so let's call this k of x minus xi. And you get the system just by saying that the vortex I is going to move according to the velocity created by all the other vortices. And again, I can put diffusion or no diffusion. This is another very old system. This was actually written by Helmholtz in the mid-19th century. And at the time, it was written with the hope of better understanding singular behavior of fluids. So Helmholtz was talking about turbulence. We would probably be a little bit uneasy nowadays talking about turbulence in dimension 2, but it's still a very important model in statistical physics. And if sigma n goes to 0, the mean field limit now I'm going to use omega the vorticity, right? Just reads something like this. And this turns out to be exactly the vorticity formulation of Euler. And if sigma n converges to a sigma that does not degenerate, so again, assuming there's only a constant, then you would find incompressible Navier-Stokes. So this was another very big question. The derivation today is at least well understood in the symmetric case. Right, so with all the vorticity equals. And there's quite a bit of there's quite a bit of work actually in the symmetric case. So in for deterministic initial data for Euler, you had the very classical papers from the early 90s by Goodman, Hu, and Lovengrop. And then Hu and Lovengrop, and there's a whole series here. For Euler deterministic initial data. Right. Their goal was mostly for numerical methods. That's why you have deterministic data. You have work by Chauchet in the 90s for random data Euler. In the stochastic case for Navier-Stokes, you have a very classical work by Ozada in the 80s. This was later improved by Fournier or Michler. And we had a work with my student. And even more recently, you have some work by Rosenzweig for Euler. But if you start putting, again, vorticities that are different, and in particular vorticities that change sign, then it's a lot harder. So this is clearly a case where the non-exchangeable system has very specific difficulties that you're not going to see if you just focus on the exchangeable system. And the last example that I want to mention here now comes more from biology. And it's a basic chemotaxis model. And now the idea is that we are going to study the dynamics of n microorganisms. And what you typically need to follow is just their position in this super simple model. And so what do? We're assuming here that there is a certain chemical attractant in the environment. And we are going to denote its concentration C. And we start with a very simple model, which is to say that those microorganisms follow the gradient of the concentration. So they try to go to where the concentration is the highest. Plus, again, possibly some diffusion. Right. So if you know the concentration C, this is a very simple SZ, right? It's not a multi-agent system. You get the multi-agent system by assuming that the chemical is produced by the organism as well. All right, and so you're going to have a diffusion equation, right? On the chemical with as a right-hand side, well, the microorganism. So something like the sum over I of whatever coefficient you want to put here. I'm going to denote them mu I and delta centered at xi. And if the velocity of diffusion is fast, right? Fast with respect to what? Fast with respect to the velocity of the microorganism. Right. Then you end up having an equation of this type. Now I rescale. I can rescale everything. Dividing by nu. And this is, of course, very, very easy to solve, right? Using, again, the fundamental solution of a Laplacian. And, well, if I put that into the dynamics, now I end up with something that is going to look, again, very, very similar to my point charges or to my point masses, except I don't have velocity, so I have directly the corresponding equation. Here. Now, the problem, of course, is this is attractive, and this is attractive at order 1, so there can be blow-ups, right? And there's a very recent paper by Fournier and one of his students where they exhibit blow up, and there was a previous paper by Fournier and Jourdain where they really tried to study the dynamics of that. So go see Nicolas for this is essentially the message here. The Minford limit is the very well-known Keller-Zegel system, or sometimes Spatlak-Keller-Zegel system. With, again, possible blow-ups. And this actually depends on the strength of the diffusion with respect to the interaction. So versus mu. And I'm not going to say much more here. The Minford limit, because of the possible blow up, we knew very, very little of it. There was a somewhat weak result by Fournier and Jourdain, but without propagation of chaos. So it was even hard to have uniqueness on the limit. And very recently, we derived it, but the paper is not yet published. It's just submitted with Brash and my students. All right. I think I will stop here for the first part, and again let you ask any questions you want.
Awesome. Thanks a lot, Pierre-Emmanuel. How about anyone else? Does anyone else have any questions?
The first part was relatively simple, I hope. Things will get a bit more technical soon, but
I actually just had a quick question about what you literally just talked about. So what happens at what happens with the limit at the blow up? At the possible blow up?
I don't know. No, so we only know how to derive the limit. So the paper, as it is currently written, only derives the limit in the case without blow up.
Oh, okay. Okay.
All right. That's something I should have said. I actually think that there's a relatively simple correction that allows to derive it up to the time of blow up. But up to the time of blow up. So in the sense that things are getting messier and messier when you approach that time. Again, Nicolas has a very, very nice construction of an actual blow up. So showing that the particle system can have blow up. So it's not only that the mean field limit can fail, it's actually that particles can collide.
Yeah.
And more than two, right? He has macroscopic blow-ups.
Yeah, tons of particles have to collapse, right?
The tons of particles collide at some time. Now, what is hard to say, though, is whether this would happen at the same time.
I was just about to ask this, and I was just about to ask if the particle limit, I guess you can derive the next order correction,
yes,
to the system at near blow up, who the high order term that would matter near blow up time, or you can't really because the particle system actually is also undergoing finite time blow up.
In general, this is something I'm not really going to talk about. We don't understand very well how to derive first order corrections to an intel limit. And there's been recent progress. What I should start saying, the big paper there is Graham Meleard, and it's a little bit older, but for Lipschitz interaction. Mm-hmm. And so with Lipschitz interaction, it does derive the stochastic system that is the first order correction in time of order one, right? Which is a different question than asking what is the correction for large time at order one, where no one really knows how to do that. Okay.
Yeah, I was going to ask if there's a clear reason to believe that that's sort of doable. Like, I don't know.
The best attempt I know of, right, was this recent paper by Duerings and Saint-Raymond.
I don't think I saw it.
Where they start getting closer to things like Lénard-Balescu, which, if you see what I mean, otherwise it's hard to explain.
Yeah.
This is probably very, very problem dependent. Which is another way of saying it's probably super messy, right?
Yeah.
And they still can't do it, okay? They still cannot reach times that are large enough to see the new system show up.
Yeah. That kind of just describes our field in general. Problem dependent, messy, and can't quite do it. So.
I only know how to do that on super elementary toy models.
Yeah.
that are not very interesting, right? But so I don't have an example where on an interesting model people actually derive the correction for large time on the time scale that would be interesting.
So I think it's a very hard problem, even for a relatively simple problem. So
yes.
But okay, let's take a 5-minute break, and then you can do your